Hello guys, welcome back to my channel Gamma. So in the last video we talked about the differentiability of multivariable functions and what criterias we had to meet in order to classify as a function as differentiable. Now we spoke about the gradient in the last video, but we didn't talk much. So in this video we're going to talk about gradient and other differential operators. So let's get started. Okay, so first of all, what do we mean when we say operator? So if there are any physicists in the house, you might have encountered operators before in quantum mechanics, the Hamiltonian operator for example, or even the angular momentum operator. Well, an operator in mathematics, at least the informal way I'm explaining it is, it's a map or morphism or function or even a transformation. Well, you may say that these terms are like synonymous to each other, but it depends in what context you're using it. So I could have put a dash here, but since we're defining operators, let me start with colons first. So from where to where, so you should have a starting place and an ending place. So from one space to another space. Okay, that's a pretty broad definition. So most of the operators that we will be working with in this video series can be represented by matrices. And if you remember the three perspectives of looking at matrices, you might recall the operator or the map or morphism perspective. Okay, first let's talk about the general differential operator. Okay. If you want, I can use another color here. Let's see. This green should be fine. Well, you represent it this way. This upside down triangle. And it's a vector quantity, so it has basis vectors associated with it. Partial derivative with respect to x. And I hope you know what partial derivatives are. If you don't, please watch the last video. So this symbol is what is called nabla or del. It depends. I mean, depends. Even I don't have a preference for this. So okay. So it depends on how you use this operator. You may, if given a function, you may choose to do different things with this operator. First thing you can do is you can apply it. So assuming you have some scalar function, let's call it phi of x1, x2, x3. What you can do is you can apply it directly. So you have nabla of phi of x1, x2, x3, and then that just becomes, well, e1 now because of these subscripts. Partial psi. It's actually phi, my bad. Yeah, my Greek is really messed up today, I think. it's a phi. So partial phi or partial x1 plus, keep doing the same for the three variables that it depends on. Okay, and now I can conveniently write this in a subscript summation convention. Say ei partial xi of phi. Okay, and this, whatever we do, whatever we did in this case where we applied it, this application of the differential operator, the del operator, is simply called the gradient. And I hope you see this is exactly the gradient that we had, because phi is just a scalar field, right? We defined the gradient to be this way in the last video. Okay, I mean, if you want, you can represent the gradient of a scalar field in terms of this column vector with each component as a partial derivative. Since this is a function of two variables, we have just x and y, so two components for the column vector. And okay, since this is a vector, it should have some direction, right? It has a magnitude, fine. We have two components. We can do the traditional magnitude of a vector formula to get the magnitude. But what about the direction? Well, it's hard to figure that out from this formulation or whatever formulation we gathered until now. But we can, when we talk about like change in a certain direction, that's when the direction of the gradient will make a little more sense. So I invite you onto the next page where we actually talk about the directional derivatives or change in a given direction. Because hey, why not? It's multivariable calc. Okay, so in this section, the question we need to really ask ourselves is, how much does I know f, which is a multivariable function, a scalar field nevertheless, change in a given direction? Okay, so the direction, I would like to denote it by the vector v, which has components, say I know v1, v2. Let's do this for like two dimensions, and you can see it clearly extends onto higher dimensions. Well, what we can do is, we want to find a change in f, right? So assume you have f of x and y. Again, as I said, let's do it in 2 dimensions. The change in f, and now we can do a little chain rule. So you have partial f over partial x dx plus partial f over partial y dy. That's fair. I mean, you can clearly see this is an extension of the chain rule in single variable calc. So fine. What do we have here? Just looking at this, you realize that this is a dot product of the gradient of f dotted with this dx dy vector, which I prefer to call the dr vector if we define r to just be the position vector x and y, then dr will just be dx dy. Okay, now we can parameterize our directions. Our direction is along the vector v. We can parameterize our direction, define a base point x naught y naught. We can define our position vector, displacement vector r to be, well, let's see, so x of t, y of t, which becomes x naught plus v1 of t, because that's the x component, comma y naught plus v2 of t. Okay, and dr is not that bad. Dr is just v1 v2 dt. Okay, fair enough. What we can do is we can plug this into this original guy now. So d of f of x of t, y of t now, because now they're parameters, they have a parameter t, becomes just, now you can do the chain rule again. And then since dx of t is depends on t, differentiate with respect to t, do the same with the y. Now plug everything in. We have partial f, partial x, v1 plus partial f, partial y, v2. This, you can clearly see this from this relation over here. Okay, you can represent this as the gradient of f dotted with the vector v. That is this. I mean, if you want to write the small d as a capital, it's fine, it's all convention. So this is called the directional derivative of f in the direction of vector v. Okay, so in single variable calculus we had one direction. In multivariable we can have many directions. So it kind of makes sense to define in what direction we're taking a derivative. And as you see, this easily generalizes to higher dimensions because you can parameterize a path. You can have x1 to xn, all functions of t, because you just want a single path. We can, you know, find like starting points x0, y0, or x1 naught, x2 naught till xn naught, differentiate them, and then you'll have more terms. You'll have to add more terms like from x1 to xn for this chain rule step, and then the dot product just remains the same, and because we will have n components as well. So you see this clearly generalizes to n dimensions. Now why is this helpful in helping us understand the direction of the gradient? That's because, let's see, let me use another color because we are talking about something else. How about yellow? Okay, so we have this. So when is this the maximum? When is the change in f the maximum? So that the question is, in what direction should we go so that we change f the most? Well, we know that the directional derivative of f in direction v is just gradient of f dotted with vector v. If you want this to be maximum, so look at this dot product. When is a dot product maximum? When both the vectors are parallel to each other. So f changes the most when we travel in the direction of the gradient. And this change is positive because if they're parallel, the angle between them is 0, the dot product will be positive. But if they're anti-parallel, then the dot product will be negative. So increases instead of this, increases most when we move in the direction of the gradient. So the gradient is sort of giving you the path where you can increase your height the fastest. I mean, this is just taking the example of a hill, assuming you have a hill or a scalar field which becomes a hill, whose level sets become a hill eventually. Then the gradient will always, I'd say, if you take gradients at like different points, the trail of gradients will always point towards the path which is steepest, that increases your height the most. That's the direction of the gradient. So now it kind of makes sense with this definition. One more important thing is, when is the change 0? When is the change in f 0? That's when the gradient, the path we take, is perpendicular to the gradient. So assuming, using the hill example again, if you take a path that's like this, you're not changing f at all by this, because you're going perpendicular to the gradient at every point, so you're not changing f at all. So therefore, if f represents the height of the hill, you're not changing height at all, so no change in height. And since there's no change in height, which means there's like a constant z, right? There's a, assuming this hill function was like something like this, since there's no change in height, it's equal to some constant, say c, which means this is along the level set at that height. So v perpendicular is along a level set. So this is one way of seeing that the gradient is always perpendicular to the level set, let's say tangent vectors. So I mean, you can do another example, I guess. Take this paraboloid, for example, x squared plus y squared. Gradient turns out to be 2x 2y. If we take, if we do some contour map of this, the level sets look like this. They're concentric circles with increasing radius. You can see by setting them equal to a constant, you get concentric circles centered at the origin. And the gradient 2x and y, you can plot this out on like MATLAB or like Desmos or something, will just be will point radially outwards. Of course, they have a factor of 2, so they're not all normalized or something, but it does the job. So they're looking a lot like this, like a spider's web. So if you notice, if you do have a tangent vector here, that's perpendicular to the gradient. So this kind of ties back to what we talked about with regards to the gradient in the last video. Okay, so we're done with our discussion of gradients. Let's look at something else. Now assume you have a vector field of x, y, and z that takes points in R3, gives you a vector in R3. So what we can do, since we have the del operator and this is a vector field, we can't take the gradient. I mean, we can, but it won't be trivial. It will be a tensor. We're not talking about that. So if you have two vectors, you can do two things with them: dot product and cross product. So first let's do the dot product because it's way simpler. You get this quantity. So if you kind of expand it out, ex partial x, ey partial y, ez partial z, dotted with let's say it has components, say f1 or fx, ex, fy, ey, fz, ez. Now the dot product yields partial fx dx plus partial fy dy plus partial fz dz, and this is a scalar. It makes sense because this is a dot product. We can try to use subscript summation convention for this entire thing. We have, say, for this we have ei partial sub xi dotted with fj e sub j hat. And now since it's a derivative, you can't take the fj out or of this. You can't commute the derivative, these partials and everything, so just keep that intact, and you have a Dirac delta of ij, a Kronecker delta, my bad, of ij. So this becomes partial xi fi, and this makes sense because in this quantity here, the index of the f and the thing it was differentiated with respect to always matched. So that's this quantity, which we will now call the divergence of the vector field f. Now okay, so we know what we can know how to calculate it. So how do we visualize this? Well, it's hard to visualize now because we haven't yet covered Gauss's theorem, but think about it this way. It tells you how much vector field sinks or sources. So assuming you have like a vector field that's somewhat like this. This is again a two-dimensional version. So there's like a source here that's like generating the vector field lines. This has maximum divergence, and something that is like a sink, stuff is going in. It has the minimum divergence. It has the least, like it's a highest negative, lowest negative value actually. So this is actually what it is. If you want to figure out the divergence, what the divergence is, what you do is, if you have like a three-dimensional vector field, you construct like an infinitesimal cube. pardon my drawing here, and you count the number of field lines that are going in and that are coming out from like all sides. So you'll get 0 if the number that went in is the number that went out. So the divergence is sort of a measure of accumulation of field lines inside an infinitesimal cube. When I mean infinitesimal, this guy is like really small. Like it's like dx, dy, dz like lengths. And this kind of makes sense because we're dealing with derivatives here, so we need to be everything needs to be a differential size or an infinitesimal amount. And why we chose a cube for this and why we're calculating the field lines passing through, cutting through the surface or whatever will be revealed once we do Gauss's theorem. Okay, so for this guy with the maximum divergence, this is given by x, y, z. Calculate the divergence. And you get 3. I mean, this is not the maximum divergence per se, because you can have some other functions and like crazy functions that like become really large, but like this is the ideal case for the divergence. Let me say an ideal case, and this is like the negative ideal case, like the opposite of that, and kind of makes sense because that's what the name suggests, divergence. So stuff must come out from from a point. This is a convergence, so think about it that way. And by the way, if you basically construct a cube in this 3-dimensional xyz, if this vector field, if we construct a 3-dimensional cube, you'll have a constant divergence, because anywhere you go, say if you're on like this boundary or something, the field lines coming in are weaker than the field lines coming out, because of the fact that you're gonna have greater xyz, so the magnitude is gonna increase at like the farther length element of the cube on this side of the cube than on this side of the cube. So even though there's it doesn't look like there's like one point where everything's like coming out, there still is a non-zero divergence here, just because of the fact that as you go farther, as xyz increases, so does the magnitude of the vector field f at those points, and that's why there's kind of more strength of vector fields on the farther side of the cube than the inner side of the cube, and that prevents the divergence from being 0, although there's no source or sink per se, like in these two ideal and non-ideal cases. Okay, so let's now talk about the curl. Oops, spoiler alert. Oh, what remains is the cross product, so I think you saw this coming from around a mile. Let's just use subscript summation for this. You cross this with say fj ej hat. So what you're gonna get is you're gonna get Levi-Civita ijk partial xi fj, this is I, my bad, and ek. So this, the way to calculate this, if you're like a true engineer, you can use Kramer's rule. So if you have partial with respect to x, partial with respect to y, partial with respect to z, say I don't know, fx, fy, fz, and then you do this determinant and you get the curl. Okay, so this is how you calculate it. Now what's the physical interpretation of this? Well, divergence was a measure of sinks and sources. The curl is a measure of rotation or rotatability of a vector field. So so the ideal case for the curl is a vector field that's, you know, somewhat like this. I'm trying to be as non-pointy as possible, while also being pointy with the vectors. Something like this. Okay. And the way to calculate or think about it, we use a cube, infinitesimal cube for the divergence. For the curl, we use an infinitesimal square loop. So way we think about it is we want the field lines to be parallel to like this orientation of this square loop. So we're counting the lines that are perpendicular to, you know, each of these segments in the arrow direction indicated, and that's how we get a measure, or at least the magnitude of the curl. The direction of the curl, because this is a vector, remember, it's a cross product. The direction is given by the right hand rule. So it's like if it's an anti-clockwise, then the curl will be pointing straight out of the page. So this is straight out of the page and this is straight into the page. So for this it will be straight out of the page, or any other rotation, clockwise rotation will be into the page, because a cross product is anti-commutative. Be sure to remember that. Now let's take this example. Let's take, I know, this simple example, I guess, of f negative y and x. The curl, it turns out, is pretty simple. Is just constant 2 easy hat. And the way this vector field looks like is sort of like this. Now, you know, it's the case at the center is pretty trivial. You construct a square loop. You see that, you know, they're pretty parallel at least at the center of these rotations. Now at any other non-centered, any off-center point, if you construct like a square loop here, there's no like real rotation that's like centered at the center of the loop. But notice this: as you go farther, your y and x increase. So on the farther side, the magnitude of the vector is more than on the inner side, as I indicated with the length of these arrows. So there's going to be, you know, like more. So this greater vector is going to force rotation over here, kind of like overpowering this other vector. So you're eventually going to get some form of rotation which is like this. Think about this as like trying to rotate this square loop. Think about torques. Well, if you have two torques but one side is more than the other, it's gonna have a dominating influence and gonna have a torque effect, a turning effect on this square loop entirely. Think about it that way. So now again, why we chose square loops here and why we chose those infinitesimal cubes for the divergence will be revealed once we do the Gauss's theorem for divergence and Stokes' theorem for the curve. Now, let me mention once again that this is an infinitesimal square loop, because again we're dealing with partial derivatives which deal with locality and infinitesimals and differential elements. So yep. And finally, let me briefly talk about the Laplacian. Okay, so again, take a scalar field, some scalar field, let's say xyz, and take the gradient of it. Of course, I just showed you how you can do that. And then take the divergence of the gradient, and this quantity we represent by now a right side up triangle delta of f, or this nabla squared, this del squared of f. This is called the Laplacian operator. This quantity del squared is the Laplacian operator, and this just becomes partial squared f partial x squared and again we can use this summation convention. It looks like we're gonna have a Kronecker delta party here. Which turns out indeed to be partial over partial xi, partial over partial xi f. And that is Laplacian of f. This is a scalar Laplacian. You can also have a vector Laplacian where you have, you know, if you have a vector potential, then you have the vector gradient, which is a tensor. So I don't want to deal with that now. The Laplacian is really important in many applications of physics. It's really important in Laplace's equation, which is just says that set the Laplacian to 0, or Poisson's equation, Laplacian to some function of, I don't know, x, y, z, anything, depends. This is Laplace's equation, and this is Poisson's equation. Both of them French mathematicians. Okay, I think this should be it for this video. I hope you really enjoyed this video, guys. Please like and subscribe to my channel, and in the meantime, stay tuned for more content, and peace out.